Hey, everyone, I'm Dr. Farouk, and today we're diving deep into the brain of your computer, the CPU. Now imagine you're trying to watch a video, download a file, and listen to music all at the same time. How does your computer not just completely freak out? The secret is something called CPU scheduling. This is the magic that lets your computer juggle multiple tasks or processes at once, making sure everything runs smoothly. It's the ultimate multitasking manager, and without it, your super-fast computer would feel incredibly slow, only able to do one single thing at a time. It's a fundamental concept in what we call multi-programming, which is just a fancy way of saying doing lots of stuff at once. Think of it like being the head chef in a super busy restaurant on a Saturday night. You've got dozens of orders coming in all at once. Some are simple salads, others are complex multi-course meals. You, the chef, the CPU, can only cook one thing at a time. So, how do you decide which order to tackle next? Do you cook the first one that came in? The quickest one? The one for the VIP table? This decision-making process is exactly what CPU scheduling is all about. The goal is to keep the customers, the programs, happy and get the food out, the tasks done, as efficiently as possible, so nobody is left waiting forever for their meal. In this video, we're going to break down the 5 most essential CPU scheduling algorithms. We'll ditch the super complex jargon and use simple, easy-to-understand examples and analogies for each one. We'll look at how they work, their pros and their cons, from the simple first-come, first-served method to more complex strategies that prioritize certain tasks. By the end, you'll have a crystal-clear understanding of how your computer's brain decides what to do next. So grab your thinking caps and let's get started. All right, let's kick things off with the most straightforward algorithm of them all. First come, first served, or FCFS for short. This is exactly what it sounds like. It's the digital equivalent of waiting in line at a movie theater or a ticket counter. The first process that requests the CPU is the first one to get it. It's polite, it's orderly, and it's incredibly simple to implement. The operating system just needs to maintain a simple queue, like a line of people. And as each process finishes, the next one in line gets its turn. No fuss, no complications. Imagine 3 people walking up to a single ATM. Person A arrives first, then person B, then person C. Under FCFS, person A gets to use the ATM until they are completely done with all their transactions. It doesn't matter if they are just checking their balance or taking out a huge sum of cash in small bills, which takes forever. Person B and person C just have to wait patiently. Once person A is finished, person B gets their turn, and only after B is done can C finally step up. The order is strictly determined by arrival time. This simplicity is its greatest strength. It's easy to understand and code, which is why it's a classic textbook example. The logic is fair in a very basic sense. No one gets to cut in line. If you've been waiting the longest, you're next. This prevents a situation where a new process could arrive and immediately get service while older ones are left waiting indefinitely. It's a predictable and stable system, which has its own advantages in certain very simple computing environments. However, this is where we run into a major problem. FCFS is what we call a non-preemptive algorithm. This means once a process gets the CPU, it holds onto it until it's completely finished or voluntarily gives it up, like when it needs to wait for an I/O operation. The CPU can't just interrupt it and say, "Hey, your turn is up." This leads to something called the convoy effect, which can be a real performance killer. Let's go back to our ATM line. Imagine person A is doing a complex business deposit that takes 10 minutes. Behind them, person B and person C just want to quickly withdraw $20, a task that would take 10 seconds each. Because of the strict FCFS rule, these 2 incredibly short tasks are stuck waiting behind one very long one. Their total waiting time is huge, even though their own service time is tiny. The overall efficiency of the ATM, our CPU, drops dramatically because it's tied up on one long job. This is the convoy effect in action. A long process at the front of the queue makes all the shorter processes behind it wait. This dramatically increases the average waiting time for everyone. It's like being stuck behind a slow-moving truck on a single-lane road. Even if your car is a Ferrari, you're forced to go at the truck's speed. The system's performance is dictated by the slowest member currently being served, not by its actual potential. So, while FCFS is simple and fair on the surface, its non-preemptive nature makes it pretty inefficient for modern, interactive operating systems. You wouldn't want your mouse clicks or keyboard strokes to get stuck waiting for a massive file to finish downloading. For that, we need algorithms that are a bit smarter and, as we'll see next, a bit more ruthless about who gets to go first. FCFS is a good starting point, but it's just the beginning of our journey. So we saw how FCFS can get bogged down by the convoy effect. How can we fix that? Well, what if we just let the shortest jobs cut in line? This brings us to our second algorithm, shortest job first, or SJF. The name says it all. When the CPU becomes free, it looks at all the processes waiting in the queue and picks the one that has the smallest execution time. It's like being at a super efficient fast food counter where the cashier decides to handle the person just ordering a drink before the family ordering meals for 10 people. The main goal of SJF is to minimize the average waiting time for all processes. And mathematically, it's proven to be the optimal algorithm for doing just that. By getting the quick jobs out of the way first, you reduce the number of processes waiting in the queue faster. This means, on average, everyone spends less time waiting. It's a huge improvement over FCFS, especially in systems with a mix of long and short tasks. The overall throughput of the system, the number of jobs completed per unit of time, goes way up. Let's revisit our ATM scenario. Person A needs 10 minutes, while person B and person C each need 10 seconds. With SJF, if they all arrive at roughly the same time, the system would look at their required time. It would let person B go first, 10 seconds, then person C, another 10 seconds, and finally, the long-winded person A, 10 minutes. The total wait time for B and C is now mere seconds instead of many minutes. Person A still has to wait, but the average waiting time for everyone involved has plummeted. It's a win for overall system efficiency. Just like FCFS, the classic version of SJF is non-preemptive. Once the CPU picks the shortest job, that job runs to completion without interruption. So, if a very long job happens to be the shortest one available at the time the CPU is free, it will start running. And if an even shorter job arrives just a moment later, it's too late. It has to wait until the current long job is finished. This is a key limitation we'll address in the next chapter. But there's a much bigger problem with SJF. It's kind of a cheater. To work, it needs to know the future. The algorithm has to know in advance exactly how long each process will take to run. In a real-world computer system, that's like trying to predict exactly how long your next phone call will last before you even make it. It's practically impossible. You can't just ask a program, "Hey, how long are you going to run for?" It doesn't know. Because of this crystal ball problem, true SJF is mostly a theoretical benchmark. It's the gold standard that we compare other more practical algorithms against. In real systems, we try to predict the next CPU burst time, often based on the previous bursts of that same process. For example, if a process has consistently used the CPU for 10 milliseconds in its last few turns, we might guess its next turn will also be around 10 milliseconds. This is an educated guess, but it's not perfect and can lead to wrong decisions. Another dark side to SJF is the risk of starvation. Imagine a steady stream of very short jobs constantly arriving. A long job that's been waiting patiently in the queue might get overlooked again and again and again. Every time the CPU becomes free, there's a new, shorter job that gets picked instead. The long job could, in theory, wait forever without ever getting a chance to run. It's starved of CPU time, so while SJF is brilliant for average waiting time, it's not so great for the poor, hungry long jobs. We've seen that SJF is great but has two flaws. It needs a crystal ball, and its non-preemptive nature means a short job can get stuck waiting. This is where our third algorithm, shortest remaining time first or SRTF, comes to the rescue. SRTF is essentially the preemptive version of SJF. Think of it as SJF on steroids. It's smarter, more aggressive, and constantly re-evaluating its decisions. It's our efficiency expert, but now they're allowed to interrupt. Here's how it works. Like SJF, it picks the job with the shortest estimated runtime. But here's the twist. If a new process arrives in the queue while another process is running, the scheduler checks if this new arrival has a shorter runtime than the remaining time of the currently running process. If it does, bam! The scheduler interrupts or preempts the current process, puts it back in the queue, and starts running the new, shorter job. It's ruthless efficiency. Let's go back to our chef analogy. The chef starts working on a complex beef Wellington that will take 20 minutes. 5 minutes in, a new order comes in for a simple side salad that will only take 1 minute to prepare. With SRTF, the chef immediately stops garnishing the beef, puts it aside, whips up the salad in 1 minute, sends it out, and then goes back to the remaining 15 minutes of work on the beef Wellington. The goal is to always be working on the thing that can be finished the soonest. This preemption makes SRTF even better at reducing average waiting time than non-preemptive SJF. It ensures that short, newly arriving jobs get serviced almost immediately. which is fantastic for system responsiveness. If you move your mouse, you want that cursor to move now, not after some background task finishes its current time slot. SRTF is designed for exactly that kind of scenario, making it feel very fast and snappy to the user. However, this power comes at a cost. The act of interrupting a process, saving its current state, all its registers and memory info, loading the new process, and later restoring the old one, is called a context switch. Context switching isn't free. It takes up a small but non-zero amount of CPU time. If you're switching back and forth too often, like if tiny jobs are arriving constantly, you could spend more time on the overhead of switching than on doing actual work. It's like a manager who spends all day interrupting employees for quick updates and nobody gets any deep work done. And just like its non-preemptive cousin, SJF, SRTF suffers from the same two major drawbacks. First, it still needs that magic crystal ball to know the future. It has to know the total execution time of a process upon its arrival to make its decisions, which, as we discussed, is not practical. It relies on the same prediction mechanisms as SJF, so its performance is only as good as its guesses. An incorrect guess can lead to a suboptimal choice and unnecessary context switches. Second, the problem of starvation can be even worse with SRTF. In SJF, a long job at least had a chance to run if it was the shortest at the moment the CPU was free. In SRTF, a long job could start running, get partway through, and then be constantly interrupted by a stream of new, shorter jobs. It might never get to finish. Imagine our beef Wellington chef getting interrupted by an endless stream of salad orders. The beef might sit on the counter getting cold forever. It's a serious fairness issue that needs to be addressed in any real-world implementation. So far, our algorithms have focused on efficiency, but this has come at the cost of fairness, with longer jobs potentially starving. What if we designed an algorithm where fairness was the #1 priority? That brings us to round robin, or RR. This is one of the most common and important scheduling algorithms, especially for time-sharing systems like the desktop or server operating systems we use every day. It's designed to give every process a fair shot at the CPU. The core idea is simple and elegant. Instead of letting a process run until it's finished or a shorter job arrives, round robin gives every single process a small, fixed unit of CPU time, called a time slice or quantum. Think of it like a group of kids taking turns playing a video game. Each kid gets to play for exactly 2 minutes. When their 2 minutes are up, they have to pass the controller to the next person in line, whether they've finished the level or not. Then they go to the back of the line to wait for their next turn. The operating system maintains a circular queue of ready processes. It picks the first process from the queue, sets a timer for the length of the time quantum, and lets it run. One of two things will happen. Either the process finishes before the timer goes off, in which case it leaves the system and the scheduler moves to the next process in line, or, more commonly, the timer goes off first. When that happens, the CPU preempts the process, saves its state, and moves it to the back of the circular queue. The scheduler then picks the next process at the front of the queue, and the cycle repeats. This approach is wonderfully fair. No process gets to hog the CPU. Even a very long process will get some runtime, then get moved to the back, allowing all the other processes to get their turn before it comes around again. This provides excellent responsiveness, which is why it's so great for interactive systems. Your web browser, your music player, and your text editor all feel like they are running simultaneously because they are each getting tiny slices of CPU time cycled through at incredibly high speed. The performance of round robin is critically dependent on the size of that time quantum. If the time slice is too large, say 10 seconds, round robin starts to behave just like our old friend, first come, first served. A process would get the CPU and likely finish before its massive time slice is up, so the next process in line gets to go. You lose all the benefits of responsiveness because the turns are too long. On the other hand, if the time slice is too small, say just a few microseconds, the overhead from context switching can become overwhelming. Remember, every time we switch processes, it costs a little bit of CPU time. If the time slice is barely longer than the context switch time itself, the CPU will spend almost all of its energy just switching between tasks instead of actually executing them. It's like passing the game controller so fast that nobody even has time to press a button before their turn is over. Finding the perfect time quantum is a balancing act. It needs to be long enough to minimize context switching overhead, but short enough to provide good responsiveness for users. A typical value might be somewhere between 10 and 100 milliseconds. This is long enough for a process to get a meaningful amount of work done, but short enough that to a human, it feels like everything is happening at once. Round robin, with a well-chosen quantum, provides a fantastic blend of efficiency and fairness. Our final algorithm for today is a bit different. Instead of treating all processes equally or based on their length, priority scheduling introduces a hierarchy. It's the digital equivalent of an airline's boarding process. There are first-class passengers, business class, and then economy. The first-class VIPs get to board first, no matter when they arrived at the gate. In priority scheduling, every process is assigned a priority number, and the CPU is always allocated to the process with the highest priority. This priority can be defined in a couple of ways. It can be determined externally based on factors like the importance of the user, the type of process, like a critical system process gets higher priority than a user application, or even how much a user is paying for computer time on a shared system. Or it can be determined internally using some measurable quantity like memory requirements, the ratio of I/O activity to CPU activity, or other system metrics. The key is that each process has a rank. Like some of our previous examples, priority scheduling can be either non-preemptive or preemptive. In a non-preemptive system, the scheduler picks the highest priority process and lets it run to completion, no interruptions. In a preemptive system, which is more common, if a new process arrives with a higher priority than the currently running process, the scheduler will immediately preempt the lower priority one and switch to the new, more important task. This is like a hospital emergency room. The patient with the critical injury gets seen by the doctor immediately, even if the doctor was in the middle of treating someone with a minor cold. The biggest advantage of this model is that it allows for fine-grained control over which tasks are more important. You can ensure that the most critical, time-sensitive operations are never delayed by less important background work. For example, a process handling real-time audio or video streaming might be given a very high priority to prevent stuttering and lag, while a background file indexing service would be given a very low priority. This allows the system to meet its most important performance goals. But you've probably already guessed the major glaring flaw with this system. It's the same one we saw with SJF starvation. What happens to the low priority processes? In a busy system with a steady stream of high priority tasks, a low priority process might never get to run. It will sit in the ready queue forever, constantly being passed over for more important jobs. It's the economy passenger who never gets to board because first-class passengers keep showing up. To solve this problem, a clever technique called aging is often used. Aging is a way to gradually increase the priority of processes that have been waiting in the system for a long time. For example, every 10 minutes that a process spends waiting in the queue, its priority might get bumped up by one level. Eventually, even the lowest priority process will age enough to have its priority become the highest in the system, guaranteeing that it will eventually get to run. So, priority scheduling is a powerful tool that gives system designers a lot of control. But it has to be implemented carefully. By combining it with preemption and techniques like aging, you can create a robust system that serves critical tasks quickly without completely starving the less important ones. It's a pragmatic approach that recognizes that not all tasks are created equal, but all tasks deserve a chance to run eventually. So after looking at these 5 different algorithms, from the simple FCFS to the VIP-style priority scheduling, you might be asking which one is the best. The truth is, there's no single perfect algorithm. Each one is a tool designed for a specific job, with its own unique set of strengths and weaknesses. FCFS is simple, SJF is efficient but impractical, round robin is fair, and priority scheduling gives you control. The real magic isn't in picking one, but in understanding which one to use for a given situation, and more importantly, how to combine them. Real-world operating systems are far more complex and often use hybrid schedulers that take the best ideas from several of these algorithms. For example, the Linux kernel uses a sophisticated scheduler called the Completely Fair Scheduler, or CFS, which is a brilliant evolution of the round-robin and priority concepts, designed to give every task a fair but weighted slice of the processor. It dynamically adjusts priorities to ensure responsiveness for interactive tasks while still getting background work done. These advanced schedulers prove that there's no one-size-fits-all solution. It's all about creating a balanced system. The key takeaway for you as a student is to think critically about the trade-offs. If you were designing an OS for a real-time system controlling a factory robot, what would you prioritize? Probably not fairness, but predictability and meeting deadlines, so a priority scheduler might be best. What about a busy web server? Maybe something like round robin to ensure all user requests get a fair slice of time. Understanding these fundamentals is the first step to understanding modern computer science. If you found this breakdown helpful and want more easy-to-understand tech explanations, be sure to hit that like button and subscribe. Thanks for watching.